Nebular Hypothesis. Proposed by Pierre-Simon Laplace in the late 18th century, the nebular hypothesis suggests that the solar system, including Earth, formed from a slowly rotating cloud of gas and dust known as a nebula. According to this theory, the gravitational collapse of the nebula caused it to flatten into a spinning disk over time. The Sun formed at the center due to gravitational contraction, while planets formed from the material in the disk through a process of accretion. Laplace's theory provided a comprehensive framework for understanding the formation of the solar system, including the Earth, and laid the foundation for modern planetary science. Planetesimal Hypothesis. Developed by Thomas Chamberlain and Forrest Ray Moulton in the early 20th century, the planetesimal hypothesis proposes that planets, including Earth, formed from the collision and accumulation of small solid bodies called planetesimals. These planetesimals were remnants of the protoplanetary disk surrounding the young Sun. As these bodies collided and merged due to gravitational attraction, they grew in size to form larger bodies, eventually leading to the formation of planets. The planetesimal hypothesis provided a mechanism for understanding how the diverse array of celestial bodies in the solar system, including Earth, originated from a common reservoir of material. Giant Impact Hypothesis. Proposed independently by William K. Hartman and George W. Cameron in the 1970s, the Giant Impact Hypothesis suggests that the Moon formed as a result of a collision between a Mars-sized protoplanet, often referred to as Theia, and the early Earth. According to this theory, the impact between the two bodies ejected a significant amount of material into space, which later coalesced to form the Moon. The Giant Impact Hypothesis provides an explanation for the similarities in isotopic compositions between the Earth and Moon, and offers insights into the early dynamical history of the Earth-Moon system. Capture Theory. Proposed by Hannes Alfvén and Svante Arrhenius in the mid-20th century, the capture theory suggests that Earth was originally part of a different stellar system, and was later captured by the gravitational pull of the Sun. According to this hypothesis, Earth formed elsewhere in the galaxy, and was subsequently captured by the Sun's gravitational field, eventually settling into its current orbit. The capture theory provides an alternative perspective on the formation and evolution of planetary systems and highlights the dynamic interactions that can occur between celestial bodies. Core accretion theory. Developed by Viktor Safronov in the mid-20th century, the core accretion theory focuses on the formation of Earth's core and its subsequent differentiation into distinct layers. According to this theory, the core of Earth formed through the gradual accumulation of heavy elements, such as iron and nickel, in the inner regions of the protoplanetary disk. Over time, these dense materials sank to the center of the growing Earth, forming a metallic core, while lighter materials accumulated in the outer layers to form the crust and mantle. The core accretion theory provides a mechanism for understanding the internal structure and composition of terrestrial planets like Earth. Gas capture theory. Proposed by George W. Cameron. In the mid-20th century, the gas capture theory suggests that Earth's atmosphere and volatile elements were captured from the surrounding solar nebula during its formation. According to this hypothesis, the early Earth accreted gases and volatile compounds from the protoplanetary disk as it swept through the surrounding nebular material. These captured gases eventually formed the atmosphere and volatile components of Earth's composition. The gas capture theory offers insights into the origin and evolution of Earth's atmosphere and provides a mechanism for understanding the abundance of volatile elements on terrestrial planets. Fission Theory. Suggested by George H. Darwin, son of Charles Darwin, in the late 19th century, the fission theory proposes that Earth and the Moon formed from a rapidly spinning parent body that eventually split apart due to centrifugal forces. According to this theory, the early Earth was once part of a larger, rapidly rotating protoplanet. As the protoplanet spun faster and faster, it eventually reached a critical rotational speed, causing it to break apart and form the Earth-Moon system. The fission theory offers an explanation for the similar compositions of Earth and the Moon and highlights the importance of rotational dynamics in planetary formation processes. Pulsar capture theory. Proposed by Alexander Wolszczan in the late 20th century, the pulsar capture theory suggests that Earth and other planets may have formed from material captured by the gravitational pull of a passing pulsar, a rapidly rotating neutron star. According to this hypothesis, the intense gravitational field of a pulsar could potentially capture nearby material, including dust and gas, which could then accrete to form planets. The pulsar capture theory provides an alternative mechanism for planetary formation outside of traditional stellar systems and highlights the diverse range of environments in which planets could potentially originate. Binary star system theory. Proposed by Witta and Quinlan in the late 20th century, the binary star system theory suggests that Earth formed in a binary star system, where two stars orbit each other in a mutual gravitational dance. According to this hypothesis, the presence of a companion star could influence the formation and evolution of planets like Earth through gravitational interactions and orbital dynamics. The binary star system theory offers insights into the potential role of stellar companions in shaping the characteristics of planetary systems and highlights the diversity of planetary environments that could exist within binary star systems. Nuclear fusion theory. Suggested by Raymond Littleton in the mid-20th century, the nuclear fusion theory proposes that Earth formed through the accumulation of material around a massive star undergoing nuclear fusion. According to this hypothesis, the intense radiation and stellar winds produced by a massive star could drive the compression and accretion of nearby material, leading to the formation of planets like Earth. The nuclear fusion theory provides a link between the formation of planets and the life cycles of stars, highlighting the interconnected nature of cosmic evolution. Electric universe theory. Proposed by Ralphie Jurgens in the late 20th century, the electric universe theory suggests that electric currents and plasma dynamics played a significant role in the formation of Earth and other celestial bodies. According to this hypothesis, electromagnetic forces could have facilitated the accretion and aggregation of matter in the early solar system, leading to the formation of planets and other planetary bodies. The electric universe theory offers an alternative perspective on planetary formation processes and highlights the potential influence of electromagnetic phenomena in shaping the structure and dynamics of the cosmos. Supernova Hypothesis. Proposed by George W. Cameron and James W. Truran in the mid-20th century, the supernova hypothesis suggests that Earth and other celestial bodies formed from material ejected during a supernova explosion. According to this theory, the explosive death of a massive star could enrich the surrounding interstellar medium with heavy elements, which could then condense and accrete to form planets and other planetary bodies. The supernova hypothesis offers insights into the origin of heavy elements in the universe and highlights the role of supernova events in the formation of planetary systems. Gaseous Hypothesis. Proposed by Immanuel Kant in the 18th century, the gaseous hypothesis suggests that the solar system originated from a gaseous nebula. According to this theory, a diffuse cloud of gas and dust gradually condensed under the influence of gravity to form the sun and planets. The gaseous hypothesis provides an early conceptual framework for understanding the formation of planetary systems from primordial material and highlights the importance of gravitational collapse in shaping the structure of the universe. Stellar dust cloud theory. Developed by Fred Hoyle in the mid-20th century, the stellar dust cloud theory proposes that Earth and other planets formed from the debris of a supernova explosion. According to this hypothesis, shockwaves from a supernova event could compress interstellar dust and gas, leading to the formation of new stars and planetary systems. The stellar dust cloud theory provides a mechanism for understanding the origin of Earth and other celestial bodies within the context of stellar evolution and highlights the role of supernova explosions in shaping the structure and composition of the universe.